Alright, Math 8 students, this is lesson 4.3, Graphing Linear Nonproportional Relationships using Slope and Y-intercept. And this should actually be a fairly quick lesson here because we have introduced a lot of this information already throughout the last couple lessons. So just quick review here, we are talking about slope-intercept form, and that is y equals mx plus b, where let's get the pen going here. Where m is my slope, which is our rise over run, so our vertical change over our horizontal change, and you can think of this as your change in y values over your change in x values. You'll see it written change in y over change in x, and we also call this our rate of change. So that's that quick review on what slope is. The b in y equals mx plus b is our y-intercept. Should have spaced these letters out a little bit more. And that is our place where the line crosses the y-axis, so when x is 0, y is b. In real world scenarios, this is our initial value. And we can think of this as our starting point for our graphs. X represents our independent variable. So any variable that does not depend on the other variable for its outcome, which means that y is our dependent variable. And it means that it relies on the amount of x, right? It is our total value, so it depends on x. Its values depends on x value. We can think about independent as our input and dependent as our output. If I put in 3 hours of work, I get out of it money. If I drive for 6 hours, I travel so many miles in distance. Okay, so now we're moving into graphing linear equations using slope and y-intercept. So we've got two graphs here, and we've got two equations, and we're going to do one together, and then I'm going to have you do the second one on your own. And so we are looking at our y equals mx plus b form here. So this would be our m, right, which is our slope. So in this case, slope is 1/2. Now that's telling me that the way I'm going to move this line is it's positive, so I'm going to move to the right. Sorry, whoops. Let's go back here. It's positive, so I'm going up 1 and to the right 2. So I don't know exactly where to start yet, so I can't do anything with that slope. So I have to look at my y-intercept next, which is b. And so this is telling me where I want to start that graph. This is telling me that I intercept the y-axis at positive 1. Make sure you pull that sign into that. So when x is 0, y is 1. So I'm going to go ahead and use that as my starting point. X is 0, y is 1. And now I'm going to use that slope of 1/2 or 1 over 2 to move. So I'm going to go up 1 and over 2. And that's my next point. And up 1 and over 2. Up 1, over 2 would take us off the graph. And I can go ahead and work backwards from there also, so I can continue my line into both quadrants. Okay, so I used my slope to determine the shape of my line, and I used my y-intercept to determine where I start my line on my y-axis. So go ahead and try this next one. It's labeled number 3 on your own. So pause the video, try it on your own, and then check and make sure you did it correctly. Okay, so hopefully you paused the video and tried this. we're going to look at this equation again. We've got y equals mx plus b. M is -3 and b is +4. So that's telling me my slope is -3 or -3 over 1. I would almost always recommend making that negative sign attach itself to the top number. As long as you're not duplicating that negative sign unnecessarily, then you can attach it to the bottom instead, but it just, in my mind, it's a little bit easier if I just keep it attached to that top number. So this means that my slope is a negative slope, and I am going to go down 3 and write 1. Okay, but I'm not sure where to start that line, so I'm going to look at my y-intercept. And b, in this case, is 4, which means I'm going to start that line when x is 0 and y is 4. So I'm going to travel along that y-intercept until I get to 0, 4, and that's going to be my starting point. And then I'm going to use my slope to move from there, and so I'm going to go down 3 and over 1. I'm going to do that again. 1, 2, 3, over 1. And then that line could keep going. And I'm just going to connect my points here. Hopefully I'm going to have a straight-ish line. Whoops, that line's not straight. Let's try that again. Oh, it's a little better. Okay, so that's a negative slope with a slope. It's a negative slope, and the line has a slope of -3 over 1, and has a y-intercept of 0, x is 0, y is 4. So that's our b here, and our slope is -3 and 1. Okay, so those are pretty straightforward. We're going to move on to a real-world scenario where we have this information and it wants us to graph what we've got. And this was kind of like that pizza skill check that we had. So a lot of the same stuff here, just connecting concepts and applying it to real-world situations. So Ken has a weekly goal of burning 24 calories by taking brisk walks. Sorry, 2,400 calories by taking brisk walks. The equation y equals -300x plus 2,400 represents the number of calories y, so there's our y value, number of calories, Ken has left to burn after x hours, so x represents hours of walking. Then he burns 300 calories per hour. So we need to identify our unit rate here, which is our slope. And so that's 300 calories per hour, and it's negative because he's burning them. He's getting rid of those calories. Our starting point is he's got 2,400 calories that he wants to burn. He's going to burn that number of calories by burning 300 calories per hour walking. So y represents the number of hours, and he wants to know how many hours it's going to take him to burn all those calories if he's burning 300 calories per hour walking. So we're going to go ahead and graph that, and I'm going to take that y-intercept here. This is our y-intercept. This is our b. So this is 0 and 2,400 is our starting point, which is right here. And then we're going to find our slope from that equation, which is our unit rate of -300x. So in this case, m equals -300, which is -300 over 1. So similar to our previous slope, but a huge decrease, right? So this is where it's really important to make sure you're looking at your units, right? So the units on this side are going down by 300 or up by 300, but the units on our x-axis are increasing by 1s. So again, those units don't have to be the same axis to axis, but they do need to be the same within that axis. So we've got a slope of -300, so starting at 2,400, 300 calories per hour. So after 1 hour, he should be at 2,100, right? And I didn't have to do any math for this because I know that each one of these units represents 300, right? So I should just be able to go down 300 and over 1 hour, down 300 and over 1 hour, down 300 over 1 hour. So that's what I'm doing here is I'm just connecting those points, down 300 over 1 hour. Now, if you didn't have a nice axis like this, what you would need to do is you could come over here and have your equation y equals negative 300 x plus 2400, and you would plug in the amount of hours that you wanted to know how many calories had been burned at. So let's say at 4 hours, we want to know how many calories Ken has burned. So we plug that 4 into our independent variable, our x variable, because that's our input. He's putting in 4 hours of work. So negative 300 times 4 plus 2400 should give us how many calories he's burned, right? Or how many calories he has remaining to burn. So negative 300 times 4 is negative 1200 plus 2400. So y equals 1200 calories. So he's got 1200 calories remaining, right? So this would be my y value. So if x was 4, y equals 1200. That gives me a ordered pair. But that's the long way. We knew we could just go down and over, which is nice. So we've got our graph. Are we going to connect our line here? We talked about this yesterday. Do we connect the lines in all scenarios? Not always, but we are in this one because we can find out how many calories he's burned at any given time. So instead of, if we want to find out how many calories he's burned in an hour and a half, we can find that number. So we can put a value in between our points by putting a line there. That's okay. We can do that in this scenario. And then we're going to answer this final question. After how many hours of walking will Ken have 600 calories left to burn? So we want to go onto our graph and find out where 600 remaining calories is. So this is calories remaining on our y-axis. We find 600. We find that point. And so at 6 hours, he has 600 calories left to burn. And that's not a complete sentence, but we're going to go ahead and leave that like that for now. And we want to find out after how many hours will he reach his weekly goal. So his weekly goal is 2,400 in a week, right? So we need to find out when he's got that down to 0 calories remaining. And that is right here at 8 hours, where calories remaining is, calories remaining is 0. So at 8 hours, calories remaining is 0, right? And we just followed that down here to our 0 point, right? 8 hours. So at 2,400 calories in a week, will be burned after 8 hours of walking. I'm just going to head right after 8 hours. This is a nice real-world scenario here because there's times where, okay, if you, for example, wanted to make a certain amount of money and you wanted to find out how many hours you had to work to make that amount of money, or you wanted to spend so much time gardening and you wanted to find out with travel how long it might take you to get someplace. That's a really random scenario. Forget that one. But if you wanted to find out, for example, how long it was going to take you to burn a certain number of calories, right? After 8 hours, so he can now plan his week and say, okay, well, I can walk 2 hours a day, 4 days a week. That's a lot, but that gives him the ability to kind of, plan his life now. So this is a real world situation here. If you have any questions, bring them to class. That's all we've got for lesson 4.3 today because a lot of this we have covered in some other lessons. So I will see you in class tomorrow. This is lesson 4.3. If you have questions, bring them. And that is it.